Good afternoon, everyone. Uh, uh, Welcome to Bose Colloquium series. It's a great pleasure to have Professor Jean-Pascal Sutter, University of Toulouse, and we have a Bose Colloquium speaker today. Professor Jean-Pascal Sutter is the research director at CNRS, and he obtained his PhD in chemistry from University of Strasbourg, France in 1992. And then he did his postdoctoral fellowship at University of Czech, Netherlands. Would that's correct? Okay. uh, and he started his career at CNRS in 1994 as a research fellow in the field of process molecular and that he is pioneer in the molecular method. And he joined CNRS coordination chemistry laboratory to lead his research team. And its research activity focuses on molecular materials, in particular magnetic and microscopic. He is also known for his various contributions in molecular magnetic, and he is also an Infosys chair professor at IC Bangalore. And he's going to talk about from magnetic anisotropy to molecular magnets and journey into the coordination by pyramidal complex. Yes. I'll first request
It's my
our
pleasure to
candidate to
felicitate you, Mr. Jean-Pascal Sutter.
Thank you very much.
Small gift. Okay.
So please,
Please do that.
thank you.
Welcome. You can take this with you. Yes. Okay.
Thank you very much. Good afternoon, everybody. It's a great pleasure for me to visit you for 2 days and to have a chance to with you and overview of what we are doing in my group. But before starting, I would like to thank, of course, the team who organized this visit, and especially Farhana, who I know since a few years now.
Many years.
Many years.
I mean,
So it's my first, also my first visit. It was a nice chance to see the city yesterday, and I had a very nice guide. Okay, so I would like to move to my seminar. So actually, I'm a chemist. I'm going to tell you a little bit about. Or actually, what I should say is I will give you some chemist view of some physical problem. Because the project I would like to discuss with you today is the approach we developed to try to rationally construct molecular nanomagnets. These nanomagnets are single-chain molecules and single molecule magnets. But before discussing that, maybe I thought it's worth introducing what is a molecular nanomagnet. Maybe not everybody is familiar with that. So I have prepared a very simplistic cartoon just to give you a flavor of what is the idea. So first of all, when you are playing with some paramagnetic molecule, like the one I draw here, and the same is true for the 1D organization of paramagnetic systems, you can see this species as a small magnet. There is a magnetic moment that in a coordination compound mainly comes from the metal center, and so you can see that as a tiny magnet with a north and south poles. So if now you have such kind of system, let's take an assembly such molecules, when you take them like that, you have a random organization of the orientation of the magnetic moment of each of these species. So a way of drawing that is to do it like that. So it means that you have as many moments oriented in one direction than in other direction. But if you apply a field, now you can turn to have all your molecules with a magnetic moment oriented in the same direction. And when you switch off the field, this is supposed to stay like that. So your system gets magnetized. At least it is magnetized as long as the temperature is below a blocking temperature. But as soon as you increase the temperature, your system relaxes, and of course, you go back to something that is a statistical distribution of these systems. And this takes place because you have an energy barrier between the magnetic moment oriented down or up. And this energy barrier, so I just take here the same picture. So this energy barrier is mainly given by the spin of your system and the anisotropy. So if you expect some molecules to behave like that, what you need is to have an anisotropy, a large anisotropy, or as large as possible. And this anisotropy, if we take the zero field splitting D parameter, actual parameter, this value should be negative. What it means is that you have the orientation of the magnetization along one axis. Along this axis, it can be up or down. And these are the two states. And then you need also a large spin ground state that is given here. And if you have a polynuclear systems, you have also to have efficient exchange interaction. So this is a little bit the basics we are using to try to make this system. So if now you go back to chemistry, what you need are building blocks with large Ising type anisotropy. And what we have been developing is systems that have this peculiar geometry, so pentagonal bipyramid. The reason is because we have in this situation with this geometry we have such kind of, we can reach such kind of anisotropy. And then you can use these molecules to put them together to obtain the spin topology, the exchange interaction, and even some other features. And this is what I would like to discuss during the coming minutes. First, I would like to tell you a little bit why this complexity or this geometry is interesting. So, bipyramid pentagonal systems are, here you can see a few examples. You see this geometry. So all these compounds can be obtained in a controlled way using a pentadontate ligand that will occupy the equatorial position. So you see here, you have the 5 atoms that sit in the equatorial position. And then you have 2 atoms in the apical position of the metal cell. So here you can have open ligand, or you can have cyclic closed macrocyclic. And actually, this chemistry is known since a very long time. So people have found how to make such kind of complexes in the 70s. But at that time, nobody was looking about magnetic anisotropy. So chemistry was known, but not what the physical properties. So in such a geometry, so what I show here is the energy diagram of the d orbitals. So this is in the ideal d5h geometry. Of course, in real systems, you are not exactly in the perfect geometry. So the reality is that you lift the degeneracy of this level, and the real picture it looks like this one. And if now you have a given electronic configuration for your metal ion, so you put the electrons, and if you are in the right situation, you can expect some anisotropy that is simply coming from the zero field splitting. So let's take just a few examples to illustrate that. So for instance, if you take nickel-2, so nickel-2 is D8, so if you fill the orbitals, you get something like that, and you reach a situation where you have two orbitals very close in energy that share 3 electrons. And zero field, the anisotropy from zero field splitting comes from the excited state. So the first excited state for such a system is when you promote one electron from this orbital to the orbital that is closest, that is this one. So from this orbital to this one, and during this process, the ML is not changed. So it means that the contribution of the first excited state to the zero field splitting, the decontribution of this state will be negative. Okay? If now you go to the second excited state, this will be one electron from, let's say, this orbital that will be promoted here. The next one will be this one. And in these states, you have a change in the ML. You go from ML equal 1 to, for instance, ML equals 2. And this means that the contribution to D should be positive. So this is, of course, confirmed by an initial calculation that puts some number on that. And here, what I show is just the contribution of the 3 first excited states I just introduced. So you can see that for the first excited state here, we have indeed a negative value, and this value is very large. While for the other ones, the contribution will be positive, but a little bit smaller. And so this is true for all the different excited states, and the expected overall anisotropy for the nickel in this geometry is expected to be in the order of -70. And what we actually obtain for this compound experimentally is very close, is -40. So, and this is true for the different ligands. I just take here a few examples just to show you that you can change the ligand here. These are change different ligands or atoms in the actual position. You see that the zero field splitting parameter is not changing. Today, the largest that has been reported for such a system is -28. That can be explained because of the energy diagram of the diode. I will come back to that a little bit later. Okay, so far for nickel. If you go to cobalt, you can do exactly the same analysis. And if you do that, what you will realize is that all excited states will have a positive contribution. This has been again confirmed by the theoretical insight. And for such a complex, usually the expected anisotropy is around 35. And this has been supported by plenty of examples because people did a lot of such kind of complexes with cobalt because the values are large. And this is what you can find in the literature. So you find values between, let's say, 13 to about to 70 well. So this is plenty of examples for cobalt. It has always been found to be positive. If you go to iron 2, D6, you get back to a picture that is very close to what we have for nickel. But now we have our 3 electrons in these 2 orbitals. And of course, this one being the closest, the first excited state will be promotion from here to here. Delta ML is 0, so we have, again, a large negative contribution. The other ones are positive, and based on theory, we expect something close to -20, and for the compound I show, the experiment value we got is -40. So a good value. Um, and what we learn also from theory is that actually the anisotropy axis shown here in blue is along the actual position. And the same applies for nickel. So it means that when you have a compound like that, you have an idea of what will be its anisotropy, because depending on the electron configuration, you can very easily guess if it will be positive or negative. It will be negative, for instance, if just considering the first excited state. Just considering this one, this will tell you what will be the sign of the anisotropy, because this is the largest function. So it's very easy to make a choice of the determine the anisotropy you are looking for, and you know also in the case of Ising type systems where this anisotropy axis is located, because it is along the apical position, or if you prefer, it is perpendicular to the pentagon. So this is something that is fixed, and this is very useful for the chemist, because now you know how things behave, and you know it before using this concept. However, what happens also is the energy of the anisotropy will depend actually on the energy difference between the two orbitals involved in the first excited state. So here I take an example where you have two very closely related complexes, but only the ligand in the apical position is changing. Here it's chloride, and here we have water molecules. And you see that this makes a difference in the splitting of these two orbitals. Here we are, let's say, a difference of 170, and here it's roughly 400 inverse centimeter. And of course, the contribution to D is inverse proportional to that. You can see this is much larger than the one we have. So this is a things, these are things you have to control or to take into account when you use, and if you want to use large magnetic analysis. So the good news for us was given by comparing these things. So this is what I showed you before. So this is exactly what you expect of this compound. But what happens if you do some chemistry? So here, what we did is we took actually this compound and we reacted with nickel tetracyanometallic. So what you do is you replace the chloride by a cyanide that is here linked to a nickel, and the other side goes again. And so this is a chain compound, but the paramagnetic center is only iron. This one is diamagnetic. So there is no exchange interaction, and then it's easy to analyze the anisotropy. And what you can see is the anisotropy found for this compound is the same. So we can do chemistry, the anisotropy is not changed, and the anisotropy is not changed because the geometry remains. Just a small thing. Now with these iron compounds, we have something that is strongly anisotropic, and the speed is getting large. We are speed S=2. So there is possibility that we have already for such kind of molecule slow relaxation of the magnetization. And this is indeed what we have observed. Here, for instance, for this compound, maybe what I have to tell first is how do we check, or how do we see that there is slow relaxation of the magnetization, or if you prefer, blocking of the magnetization at low temperature. For that, we use a dynamic susceptibility. So AC susceptibility data, and what I show here is the out of phase susceptibility, so chi-second, versus the frequency, the test frequency we use for the measurement and for different temperature. And what you in these curves is that what is important is the maximal threshold. And you see that the maxima of the curve comes to lower frequency as the temperature is decreased. Because it's difficult to see here, but if you go from here to here, actually we reduce the temperature. And what this means is the maxima actually is a flipping rate. And since the frequency of the maxima decreases, it means that the flipping becomes slow. So we have this slow relaxation of the magnetization, at least till a given temperature, and then the maxima stays at the same frequency. And from such kind of data, we can extract relaxation time. And if we plot the relaxation time here versus inverse temperature. And what you can see is, first we have a behavior that depends on temperature, and then we have something that depends no more to the temperature. And this is typical for a quantum tunneling effect, whereas this is a temperature-induced relaxation. We can analyze that and extract an energy barrier, and here you have the number we have obtained for this molecule. And this is something we have found for several of these molecules. I don't want to show much more about that, just to tell that very often, actually, what you see is something like that, telling that you have very fast relaxation, okay? Quantum relaxation effect. And this is because in a lattice, you have intermolecular interaction. But for chemists, this is not really a problem.
What is limiting this to 103.15? Temperature, you cannot go beyond certain temperature?
We cannot go below 2. And also it's a matter of frequency.
So it's high temperature.
Yeah. Oh, because the signal is vanishing. So relaxation is so fast that we cannot manage it. And even here we have 10,000 hertz, but very, very fast. So what I was telling is sometimes the slow relaxation is limited by the intermolecular interaction that makes the relaxation very fast. But you can organize your molecules in the solid by doing a little bit of chemistry, and this is just a molecule I showed before. So you take this one, this is the behavior. You organize it in a solid. So now you space the paramagnetic molecule, you space them in the chain, but you space them also interchain. And then the behavior you get is this one. This comes from the same molecule. It comes from this center. It's the same than here, but because there is no intermolecular interaction, now you have a clean behavior that is the one you expect, and that corresponds to what I have shown before. The numbers are there. So this is just to highlight that. And the second interesting point is that it shows that you can do chemistry without losing the intrinsic property of this complex because the geometry is there. Okay, so this is just to sum up what I was telling. So to us, what was interesting is, of course, the iron and the nickel complexes for which we have large uniaxial magnetic anisotropy and a very good structural robustness. So you keep the properties you have in your starting material, and this is the ideal situation if you want to construct polynuclear system controlling the what you put in your system. So next step here was to use these molecules as building block and try to make chain compounds, because this is our main interest. And when you do that, you need to implement some other aspects. Of course, you have to make sure you get the chain. This is you have to control the chemical topology, but you have also to use a second unit that will help to implement exchange interaction, and this exchange interaction should be strong or magnetic, or depending on what you are looking for. And you can also then add some additional feature I would like to discuss in this. So just a picture to show that it's quite easy to make polynuclear systems that behave as a single molecule magnet. So here I show antinuclear system that is obtained by reacting the complexity I have introduced before with a cyanometalate. Here it's with a tungsten CNA. So this center has a spin half, and when you react it with the iron complex or with a nickel complex, you get the same kind of compound, and these compounds behave as a single molecule. So this is just what you expect. If you do same with cobalt, you have the same structure, but you have no single molecule magnet behavior, simply because the cobalt is not allowed to lab, because cobalt has planar anisotropy, positive D, whereas this iron or nickel has a negative. So everything is right, everything works like it was expected.
So here the tungsten have spin
Spin half.
spin half.
Spin half. So we have a ferromagnetic exchange between the two species here and here. And for the nickel exchange interaction is quite large.
So these things in tungsten, there's no.
No. Isotropy comes only from the seven coordinated centers, nickel or iron. So here the second partner is just to link and to introduce exchange interaction between them. So I told you my interest goes for chain compounds, but we look also some smaller molecules, and by doing so, we realize something. This is what I would like to comment here. So, so these are the, let's say, the two building blocks we are using. So this is the one with iron that introduces the anisotropy, and this is a chromium cyanide that is used as linker, and that will provide ferromagnetic exchange interaction. So when you do this reaction in given conditions, you end up with three nuclear species that is shown here. So you have two chromium linked to the iron. So the plot here shows T versus temperature. I don't know if you are familiar to T. It's just a different unit for mu effect. More familiar with that. But what you see is as you decrease the temperature, T increases, and this is a sign of ferromagnetic. So indeed, we switch on ferromagnetic exchange between these centers, and for this compound, we can confirm that we have still a large negative magnetic anisotropy. And you understood now the story. When you have that, you can expect slow relaxation of the magnetization, and this compound is a single molecule magnet. So we have made different compounds, very similar. The difference between these here, from a chemical viewpoint, is that we have changed the air group that is here. So in the example I discussed before, this is the air group. Here we have a cyclohexyl, and here we have an NH2. And in all cases, we have the trinuclear species, but when you look to the magnetic behavior, well, this is a compound before, single molecule magnet, and this one, very fast relaxation. And the third one has a behavior that is in between. But here there is no difference between the anisotropy, there is no difference between the composition of compound. So it was a little bit surprising to us to see. The only difference here is, as you can see, is the molecules are more or less linear or a little bit more bent. And if we look to the, for instance, to the angle we have here between the carbon, nitrogen, and the iron, you see that we don't have something that is linear, and it is more or less plane. But usually people consider that this is something that has no real importance. Such a bending should not have an effect on exchange interaction and on an isotope. But to have a, let's say, some insight on that, we made some calculation. Actually, the result is the angle is important. So here we have very small angles, and what you can see is we have an exchange interaction that is much larger than what it is when there is a strong bending. And the same applies for anisotropy. So in this system, the iron, the anisotropy is -25, and here we come down to 10. And now we can understand why this is a single molecule magnet and this is not a single molecule. Because we lose exchange interaction and we decrease the magnetic anisotropy. So,
just related to the IT versus temperature curve, do you have the image curve?
yes.
So how does it look? M versus H.
N versus no. We have something that is almost linear.
You don't observe any distances in there.
Not at this temperature. You will see later I have some. But here, for this species, we should go below 2 K.
Okay.
We are still at too high temperature because.
My question is, how do you confirm that it's a ferromagnetic?
This is given by this behavior. So the chi-T increases, and the chi-T increases because the magnetic moment of this species becomes larger. Here, the ground state is a spin 5. So the ground state for this molecule is spin 5. So you expect the magnetic moment that is much larger than the contribution of the isolated state.
In this case, chromium does not give you an isotropy because
it's very big. So we choose chromium because we knew that chromium will help to have a good exchange interaction, and that this exchange interaction will be formed. So this is why we choose it.
What's the valency of chromium? One shell is filled, but there is no anisotropy.
Actually, there is no anisotropy because if you put your 3 electrons in the energy diagram I have shown before, you have 1 electron per orbital. So this is not a good situation to get a large anisotropy because to go to an excited state, the difference, the energy difference with the state you are going to populate, the orbital you are going to populate is very large. So if the energy difference is large, the contribution to anisotropy is very big.
What is the local crystal T?
Same for me.
So in these calculations, is the spin orbit component perfect?
Yes. So here it's mainly 0 to speed. Okay, so we have to take into account this bending at least. If you can have something more linear, it's better. And this is something we try to manage by playing with these air groups, because what we try to do is to introduce steric hindrance here between this group and the group of this thing. And this helps to bring them more or less in a linear. Okay, so single chain magnets, which are the goal of this project, are very closely related to molecule magnet, that is what we want now to get in this kind of system is all the magnetic moment aligned in one direction and in an energy barrier to go from this situation to this one. But the main difference for the chain system is that in this energy barrier now you have two contributions. You have the contribution I have introduced before that is coming from the anisotropy. But you have also a contribution that is coming from the exchange interaction. So in such a system, so what it means is in such a system, like before, you have to have large anisotropy, but you are also looking to get large exchange interaction because the two contribute to the let's say the barrier for the splitting of the magnetization. So if you want to construct such kind of system again, what you have to do is, like before, introduce the same, take into account the same idea. So this is one of the very first single chain magnets we have obtained. So this compound was made with iron complex that was used to introduce the magnetic anisotropy, and here we use nodium cyanate as linker, and what we get is a chain compound. Here is a simplified view of the same. So this is just the direction of the chain, and we have on the side of the chain we have again some terminal ions. For this compound here, we have quite large exchange interaction. So this is what we wanted, and of course we have also the slow relaxation because we have anisotropy. So here, this is what I have discussed before. So this is out of phase signal. So it's typical for slow relaxation of the magnetization. And another feature for the blocking of the magnetization is blocking of magnetic hysteresis. This is shown here. So for this compound, we could see that below or at 1K, we have a magnetic hysteresis. So in this plot, what I show is the magnetization versus H in one direction, and the applied field in the other direction. And you see when you go up, down, you do not follow exactly the same. So for this system, we have the hysteresis that tells you that you have a dystability. Okay? And when we analyze this data, we get an energy barrier of 74. So we're quite happy to have this behavior, but I was disappointed because I expected values that would be much larger. And actually, the reason why this value is not larger is depicted here. So here, the red arrow I show are the direction of the local magnetic anisotropy. And what you can see clearly from this picture is that the local anisotropy are strongly tilted. So this is not a good situation to have a large macroscopic anisotropy. What I mean by macroscopic is the anisotropy of the chain. And
the anti-millikelvin, why this so this less number of data points?
here,
Yeah.
nowadays, the physicist who did this measurement is calling that an avalanche. That means you have at a moment you have a very fast flipping to another state, and this is why you see this kind of steps. So what was clear here is we have to align the magnetic anisotropy of the cell. And actually, this was done by using this building block I have already introduced before. So why? Because in this case, we have a perfectly trans cyanometallic. So if this piece is linking other penters, it has to be linear. In this case, you see that the zigzag arrangement here is because the cyanide are not just opposite. we don't have 180 degrees. You end up with something that is this kind of zigzag arrangement. So when it's perfectly linear, like here, you end up with a chain that looks like this one. So this compound has been made with nickel. So you just mix these two and you crystallize your compound. And you see already here that we have something that is quite linear. And this is what I show here. I took the pentagonal plane as a reference, and you can compare the angle between the plane in pink and the plane in yellow, and you see that they are almost parallel. So we have just 4 degrees. So this means that now the anisotropy axis that is perpendicular to that plane, these axes will be aligned with the same direction. So these are just some plots of the magnetic behavior. So here we have a typical behavior of a ferromagnetic chain. You see that as the temperature decreases, we have an increase of kT. This is MH curve with a very fast increase for very small field, again characteristic of a large magnetic moment. You can analyze this data to have an idea of the exchange interaction. So we find numbers around 8 inverse centimeter. And actually, the initial reason why we made the trinuclear species, so this is a trinuclear species made with the same building blocks, is because we wanted to have a precise idea of the exchange interaction, because for such a species, you have exact model to analyze the data. This is just the behavior of the trinuclear system. So this confirms that it's ferromagnetic. The red curve is just the fitting, and the value we extract is in good agreement with what we get for the chain.
What is the ordering temperature here?
Yes.
Magnetic ordering.
There is no order. Oh, it's just chain behavior.
Just change.
It's just chain.
It remains, if never goes to paramagnetic.
No,
Always remains to the very magnetic.
in this case, I will show you later, there is no interchange. So at least down to 2K, that is the temperature we can reach, we don't see a three-dimensional order. We just see the behavior of the chains. One-dimensional magnitude.
So in the previous case where you observed the hysteresis,
That's also coming from the chain.
so that means you're saying there is no long-range order.
No, it's only the behavior of the chain, and the hysteresis is because you can you block the temperature, the magnetization of the chain in one direction, and it doesn't fit. To fit, you have to apply a stronger field to reverse the magnetization. This is why you have this system. And you will see in a coming example, and even later, in the last example, I just 3D ordering. And you will see it's a clear signature. Which,
Then why there is a saturation? There is no domain. And what is the saturation?
because when you chain is magnetized, you cannot go further. And these are real systems, so you will have a finite magnetization, because even if you have very long chain, at the moment they will stop. It's not something that is really infinite. You have a large number of sites. Okay.
So can you please explain from the chi-t versus t behavior, how do you get the ferromagnetic branch?
How we get?
What is the fitting then?
Oh.
Chi-t versus t?
Yes, here there is a model that is that has been developed for chains, and you can very easily fit. So we fit only, let's say, in the high temperature domain, because the model does not take into account the anisotropy, and so you cannot fit everything. So I don't remember, but I think here we stop around 10 or 15. So this was just to show that from such data we can also extract what I introduced before, that is a population energy, because when the exchange interaction comes into play, you have an exponential growth of the magnetization of your system. And so this is the log of pi t versus inverse t, and this is the linear part. And if you analyze that, you get the stabilization energy coming from the exchange.
So, what I think the confusion, like what he is saying that pi into t, which is just revise this. If it is a no, it will go to zero.
Yes,
Now,
yes, it is.
if magnetic movement is zero, that
Except that at a very low temperature, you deviate from that because of the
Yes.
energy. Yes.
so that's
But
what I'm saying.
hence-
You're getting some ferromagnetic interaction
Yes.
from this data, right?
Yes,
So that,
yes.
that is using some model.
Yes, yes.
You're using some J.
Yes. But this is also obtained from the blue data you can see here, that are the experimental data. To have something like that, you can only confirm interaction. But we have also the NH. I don't know if I show it, or I don't show it. But for magnetization, we have also information. It's ferromagnetic or antiferromagnetic.
So if it is antiferromagnetic, it goes down.
So the value will be smaller.
Oh, okay. Still goes up.
No, if you take an MH, M versus H, let's take this one. So let's say when you go to saturation in in just a paramagnetic system, you have two things. What you should see is something going up, and after you saturate. So here it is like that because of the energy. Anyway, here you have a value that will go to the magnetization at saturation, or height. And this value here depends on whether your system is ferromagnetic or antiferromagnetic. Because if it's ferromagnetic, the contribution here will be larger than what you have when it's antiferromagnetic. Because you have a magnetic moment that will be smaller. And depending on the spin systems, you can easily calculate. Okay. So this is another way to confirm that it's ferromagnetic or antiferromagnetic. But even for that, if it would be antiferromagnetic, what you expect, for instance, for a ferromagnetic system. For a ferromagnetic system, you have something that looks like that, except that at the point it goes down before coming up. And the first decrease, this is a sign of the antiferromagnetic interaction. Till the correlation length becomes very large, and then the magnetic moment of your system, even with the antiferromagnetic coupling, becomes large, and the moment is growing. But for a ferromagnetic chain, so ferromagnetic means you have antiferromagnetic interaction. Your centers, it should first decrease before increase. Whereas here we have a continuous increase, and this is characteristic of ferromagnetic. Okay. Okay, so for this system, of course, we have the expected AC susceptibility data. So you recognize now the plots I have shown before, and we have a single chain magnet with energy barrier of 54, just a number. So this is for nickel. So we can do better if we increase the spin of the nickel center. So we can move from nickel to iron. And, of course, we did. So we have the same kind of arrangement. I don't want to detail that. Here you can see this is the local anisotropy of each of the centers, and what you can see is they are pointing really in the same direction. So the tilt between these is very small, so they are almost something that is in the same direction. Here we have again the same behavior I have shown before. So you have been asking about the intermolecular interaction or not. So in this plot here, what I show is the susceptibility versus temperature, and you see here the plots when reducing the applied field. And what you can see is that in this system, we don't have interchain interactions. Because if we would have, let's say, antiferromagnetic interaction between the chains, so when you reduce the field, actually, this should come down. And it doesn't come down because there is no interaction, no antiferromagnetic interaction. And for this system, again, we have single chain magnet behavior. You can analyze this data. I don't want to discuss them. Just let me go just to the number. Now, the energy barrier here we have is about 100 K. So just playing, and this is the magnetization, so hysteresis pole. So here now you see that we have an opening of the hysteresis below 5 K. Quite high temperature, we have blocking of this system, and this is because the anisotropy of the chain is now very large. So we can magnetize the chain and stay magnetized below 5. This is green 3, and the blue curve here is. So this was just to show you that when, let's say, when we chemists have to design such kind of system, we have to take care about several things to optimize the problem. Of course, you have the spin center that is important. You have the anisotropy that is important. But what is important too is how this anisotropy is organized in space. And this is just a summary of what I showed you before. So here we did not take care about that, and here we took care about it. And we have almost a factor 2 in the energy barrier of the system. Okay, so now we know how to construct single chain magnets. We know how to control the anisotropy. So we go a little bit further, and we try to add some more complexity to the system. And by doing so, of course, we have in mind having new properties that can be related to the magnetic field. And what we are doing currently is we are trying to make chiral symmetry. So why chiral single chain magnet? Because we are looking for magneto-optical. I'm not going to discuss that today, so it will be too long and too early. But what I would like to show you is how the chemist can control the synthesis of a chiral single chain magnet. Of course, if you want to do that, if you want to control chirality, you have to play with chiral systems. And this means you are going to use a chiral building. So here is an example of a molecule we are using. So what we do is actually we use a pentagonal ligand that is very similar to the ones I've shown before. The difference here is that the ligand is chiral. So we have introduced here and here chiral cells. And so we can do the synthesis with one enantiomer. So we control the chiral. So here is one of the substructure of one of the complexes that has been done with the ligand that has SS stereochemistry that is shown here. But when you play with chirality, you have always two species, and you have also the same compound, but now with stereochemistry, you get the same compounds, except that this one is the mirror image of this one. But everything else is same. And you can now make extended structure. Let's take this molecule, you react it with a cyanometalate. Here's the example I showed is with nickel CN4, and you develop a chain. And here what I plot is just the let's say the chain structure in which I show only the centers, and I put a link between them. And what you can see is we have, if we start with R enantiomer, so with this one, we get a helical chain that is left-hand turning, and if we do the chemistry with the related S, we get the same chain, but now the helix turn is a right turning. So here now we control the stereochemistry at the metal center, but also at the supramolecular level. This is optical properties, the CD spectra of the two species, just to show that indeed we play really with two enantiomers.
So these two are solid or
Sorry. So let's say you do the synthesis in solution, and after all characterization are solved.
These are stable at room temperature and air stable.
Yes, yes. This one is air stable. So this is a crystal structure, and this has been recorded on a photosynthesis in air. Of course, it depends on the stability. Sometimes you have to work on the nitrogen because, for instance, iron is sensitive to oxidation. So we keep it on the nitrogen, but with nickel we don't have any problem. So this actually here with iron, this was done on the nitrogen to avoid oxidation. So we can also investigate the magnetic properties. So we do that just to have an idea of anisotropy. So this is the anisotropy of the iron center. And again, we just get what we expect. So, the previous example, the nickel was diamagnetic. So what we try to do is also play with exchange interaction and with paramagnetic space. So I would like to show only one example here. This piece is a little bit more. But was a little bit funny because we did not expect this. What I'm going to show. So here, what we used as assembling unit was actually iron Cl2. So we have this complex. So we have the iron complex with two chlorides. So this is the formula. And then you mix it with iron Cl2. And what happens is, in the reaction, you form iron Cl4, that is here, that shares one chloride with the iron that is in the parallel unit. And the same is true on the other side, and you develop a chain. And this is a picture of, let's say, the chain. I show here only the coordination for the metal centers. And so you have a chain in which you have 7 coordinated and tetrahedral iron, and these identical. And in this, for this compound again, because we start with a chiral building block, we can make the R and the S system, and the two are just each of the optical isomers you may expect of this chain. This is a chiral chain. So for this system, since we had the two irons in some geometry for which we expect some magnetic anisotropy, we look to the magnetic anisotropy through calculations. Okay? And this is a result of the calculation. So for the tetrahedral shaped iron, the anisotropy is positive, the order of 15 wave numbers, whereas in the 7 coordinated iron center, we have an anisotropy that is as expected negative, but it is very large, almost minus 30. And the reason of such a large anisotropy is this is the energy diagram of the d orbital. And I don't know if you, let's say, what happens in this system is that the ligand field in the apical position is getting very big. And this stabilizes all the orbitals that have a Z component. So this means that these two orbitals come down in energy like the Z2, and this one are up. So we have the strong negative contribution coming from these two orbitals involved in the first excited state, but the subsequent excited states involve orbitals that are very high in energy. So the positive contribution is very small. And so here we have a system that is has a large negative anisotropy because the positive contribution is just a comment. So here now we have a chain where we alternate negative and positive anisotropy, and this is a homometallic chain. Only iron chain.
YZ and DXZ are not at the same energy,
They are very close in energy.
but very small energy.
They are very small.
That's why you have very large.
Exactly. We have very large here because if now you send one of these electrons, let's say to this orbital or to this one, the energy gap here is huge. And so the anisotropy is inverse proportional to this energy. And so this means that it's mainly the negative contribution here that comes in. So this is just a picture of the anisotropy in these centers. So just to show that, again, we have the actual anisotropy of the semi-coordinated system that is perpendicular to the pentagonal plane. So you see this one here on the other line. This is a magnetic behavior. So what we see here is roughly the behavior you would expect for a ferromagnetic system. That is a system for which you have antiferromagnetic interaction. And this is shown by the decrease of IT. So it comes down to a given value and then it goes down. And this is typical for a ferromagnetic chain. So you can analyze this behavior to extract the exchanger. But what we see also for this system is that actually we have an interchain interaction and we have a magnetic orbit. And this is actually shown by the fact that we have here something that suggests magnetic orbit. Okay, this is better shown here. So this is AC susceptibility, and what we see here, this small signal shows a kind of a peak that is for any frequency. It is seen at the same temperature, and this is a sign of a three-dimensional. So for this system, we have a three-dimensional, but we also see the behavior that is coming from the chains. And actually, what we see here, this is mainly the slow relaxation process of the chains. And again, we can analyze that, and we can extract the energy barrier. And what we have here is a compound that is a constant antiferromagnetic single chain.
So how do you have done some neutron strip? How do you know it's canted and canting angle?
How you explain the magnetic field? We have the same spin. So it's because we have an anisotropy, and this anisotropy is not aligned. If it would be aligned, you would cancel the local moment. And so if you don't cancel, it means that there is a continuum. And this is why we see this. But you're right, we should do neutron experiment. But we are not used to these experiments. But this would be a good way to prove it. But just the magnetic behavior tells you that you have
But you have fluorine, there are two iron sites, right?
yes. Yes. But the two iron have set spin. Into the homometallic system is the same spin. The only difference is one side has a very large IZ type atom. And all the magnetic features are coming. Yeah, this is what I sum up here. So we have I showed you that we can introduce chirality to make a chiral single molecule magnets. But what is very interesting is to me in this system is that now we have a way to introduce anisotropy on each side.
But can you do? Can you make single crystals?
Yeah, this is actually structure is from the single crystal.
Single crystal. So you could do magnetic resonance on a single crystal. Very small.
So the drawback of all this thing with iron is we are not able to go large crystals because the energy of the bond with iron are large, and so this avoids this limits the possibility to go. Because to go large crystals, you have to have an equilibrium between solid and liquid crystal, and this is not the case here. So we have a very fast crystallization, and the result is a few hundreds of microns. So crystallography, EPL, things like that could be enough. But to make a sample for magnetometry, or at least it's too small for the setup.
What about the nickel? Nickel crystals are very small. What about the nickel?
For nickel, we get larger crystals.
How about the use the single single crystal transformations? Does that work? Like for example, you just take the nickel crystal and rightly place the nickel with some other method.
Because to change it, these are compact structures. Because what you have in mind is often framework structure, where let's say the metal ion can go in the structure, and you can have an exchange on a given side. But here it's not possible because the crystal is compact. And so if you do that, you make the best you change just on the surface, or you destroy your crystal to go on normal. So I don't remember where I stopped here. Yes, so here now we have a way of playing with the anisotropy sides. Of course, here we have positive and negative, which is not the best situation. So what we are currently doing is try also to use here a center that would give negative anisotropy, and then we expect to have better. So this is the summary of what I was telling today, or let's say a summary of the important thing I would like to stress. So with these pentagonal bipyramid complexes, you have access, very simple access to a controlled anisotropy with d values that can go from -30 to +30. So this depends on the metal ions you are going to use. With iron and with iron 2 and nickel 2, we have large Ising type anisotropy. So this is really useful for trying to make the compounds we are interested in. That is a single molecule or single chain magnets. And these complexes are also well suited for the construction of 1D system because you just exchange the optical position. So this is a good situation to make a 1D system. And it's also, because of the ligand, it's also a very versatile platform to introduce some other things like carbonate. And the message about the construction of a single molecule magnet and single chain magnet is that it is very important when you design this kind of system to align the magnetic moments because it has a very significant contribution on the energy barrier of those two layers. And also, when you use a cyanometalate, the bending of the coordination bond can also be important and should be. So this, just to mention the people that have been involved in this work. So you may see many Indian names. This is because this project was developed through a CFIPA project I had with Professor Ramashesha and his group. So these are the people, the PhD students of the group of Ramashesha that have been involved in the modeling of this system. When you have large systems, it's difficult to do modeling. So there are no simple to use models. You have to work with people that have the possibility to do that, and the group of Ramashesha and today colleague here is able to do that. And all this work, all the understanding of what was going on was possible through theoretical calculation. And this is the group of Nathalie Guéry and Nicolas Yo in Toulouse. We are collaborating since a very long time. Thanks to their inputs that we finally understood and now control these things. Just to tell you where I'm coming from, so this is France. You may know Paris, that is located here. I'm coming from a city that is Toulouse, and Toulouse is right in the south of France, so there is something like 700 kilometers between Paris and Toulouse. And I'm coming from an institute that is called Coordination Chemistry Lab, and this lab belongs to the CNRS, that is a French research organization. And in this lab, we have there are something like 200, 250 people working, staff and students. There are 13 research groups working in different topics related to coordination chemistry. That goes from catalysis and organometallic to molecular materials, like what I'm doing, but also bioinorganic research. And this is just some pictures of the city. So, Toulouse is an old city with some very nice buildings. And Toulouse is also the main center of Airbus. So something very important. And so finally, we have to see.
I saw that most of the chain magnets, right, are described by two spin interactions. Can you have more than two spin? One spin.
What do you mean by two-spin?
Like your Hamiltonians, when you model this are on the form S dot x.
Yes, yes.
Can you have S dot s times S dot s? This kind of
Actually, this is a question for you.
no, in your
No, we are using that because we have two spins in the system. So what I'm showing is mainly system that is chromium ion, chromium nickel. So this is a repeating, and this is usually also the models. The models I'm using when I use.
So what I'm trying to say is that can you change coordination number instead of having two, have four, or more, like something on
And then you use different species. Then you use different species. Now let's say if you do so, you have to change the building blocks where we are using is not adapted anymore. Because with this one I can just connect it.
And the other question would be, can you have when we take it in lattices, right? You have other kinds of interactions that you can, like DM interaction. And of course, we will be hearing about giant interactions from big areas. And those kind of
I think it's possible. But again, this is not my field, so these are things I discuss with people that are not physicists. But you're right. For instance, in this kind of systems, you may expect also some anisotropic exchange.
Yeah, supposed to be.
yeah, correct.
Should be. Any other question?
definition of D. So essentially, you took the ground state, you just take the highest occupied level, or you take all the orbitals which are occupied, then look at the excited state.
So you are again asking a question I'm not able to really to answer. What I understood from my colleagues is they take into account many levels. Usually they do calculation to know how many they have. And once they see that it doesn't change anymore, if they go to higher level calculation, they stop. But it's always something that's quite handy because it makes sense. And it may also be very tricky because, so here I only discuss systems for which we have almost only zero as a contribution to another. There are also species in which we have a first order spin on it. Then it's a choice.
What is the main motivation? You have any application devices?
So let's say for the people in the domain, one initial motivation, or still a motivation, and it's what we use when we sell a product, saying that we are playing with very small systems size, and they're bistable, so they could be the active part for the data storage. Okay, so this is what we use when we sell this project to an agency to get some money. Yeah. The reality is actually what I was telling here, what now looks very easy to handle. 10 years ago, we did not know anything. We did not know how to control the anisotropy. We did not know what to expect, what the anisotropy to really expect, I mean, numbers. The theory was known. The crystal field theory, the ligand field theory tells you that it should be positive, negative. But actually, chemists did not know how to control these things, what to expect. So for me, the main motivation is also the knowledge, the basic knowledge. And when you know, when you understand, then you can play. So for me today, this is very simple, but it was not the case for me. And when I said to me, it was also to the whole community. And what is still a very difficult topic is the literature in the recent years was full of reports, values of anisotropy molecules, and usually single atom center to getting large things. But if you want to construct a system that is more complex, like chains, these molecules are useless because the large anisotropy is because the people reached or could reach a symmetry that allows like large anisotropy. But when you look to this molecule, they're dead. So if you try to do chemistry, it will not, it will work. But the compound you will introduce, the molecule you expect to introduce in your polynuclear system will be different. Because what I have in mind is to have extremely large anisotropy. The best is to have just an action field, a two-coordinated system. In that case, you have a very small ligand field, and you are in a situation where you have first order spin-off. Of course, to have that, there should be no distortion. But the chemist can play with things to get that. So you have an extremely large analysis. But if you take this molecule, you want to do chemistry, introduce it in the chain, you end up with something for which the surrounding of the metal will be completely different. You are just using the initial analysis. These are things that playing with, especially with this. So there's still a lot to learn for the chemists, to learn how to control it. And once we know how to do it, then it goes to heat. Then you can control it.
So how do you experimentally measure D?
Mainly from magnetization. We showing that here. Yes. So what we do here, so the dots here are experimental data, and then we just feed this data with a model taking into account the zero fit splitting effect, and this gives you then a G. This includes a G and the E parameter, so the actual and the rounded zero fit splitting parameter. And when you get good fits like that, you know that your system is mainly governed by zero fit splitting, and you get the right numbers. So today we mainly use that. When we started this project, we did also high field nuclear measurements, just to confirm that magnetization was in line with what we get of high field nuclear, but also for communication. And now we know that because this is easy to make.
This works very fine.
It's very easy to make, and we know that the values we get. But once the fitting is not good, and the fitting is not like that, there's something else. And often in literature, you see fits that are not very good. So it means that the value that are given.
But if you have hysteresis, how do you
There is no hysteresis.
M versus H?
There is no hysteresis. Because for let's say for such, this is just one molecule, just one metal center, iron, and so for such a species you do not block magnetization at the 210. Because you see, I can go down to 2. At this temperature, it's not blocked. It's not blocked. Or you have to sweep the field very quickly, but then you say this is.
In one plot, you were showing the chi was increasing with decreasing magnetic field. Why do you like? How do you explain chi decreasing?
Because when you reach the saturation, you reach the largest how should I say, the susceptibility you get it by uh, delta M versus the field you are using. But this is correct only if you are in a domain where you have a linear growth of the magnetization with the field. But if you reach a system with a large field, with a large magnetic moment, it's very easy to be out of this regime because you saturate the system. This is why we measure to lower this lower.
So chi is EMU per Tesla.
For the interest of time, let's stop it here. We can talk during the tea time. So let's thank the speaker for coming.
Thank you.